All right, guys, moving into the second part of 13.1, now we're getting to what we really wanted to talk about right here, special right triangles and how that relates to trigonometry. So, special right triangles are two things that you guys learned last year in geometry, but you might very well have forgotten about. The first of which is called a 45-45-90 right triangle. So let's talk about what that looks like, guys, and I thought I would draw this out with you. So a 45-45, that's weird, 90 right triangle is named so because of its angle measures. So we've got a right angle right here, there's the 90, and then the other two angles are both going to have a measure of 45 degrees. And as I'm sure you guys remember from last year, the three angles in a triangle always have to add up to 180 degrees. So 45 plus 45 makes 90. That added to another 90 is going to get us the 180 degrees that we were looking for there in total. Okay, so with that in mind, that's what we're dealing with. And another thing I'm hoping you guys remember from last year is that in a triangle, if you've got two congruent angles, here the 45 and 45, the sides that are opposite from those angles have to be congruent to each other as well. So this leg over here on the left and this leg on the bottom have to be congruent to one another. A 45-45-90 triangle is the one and only isosceles right triangle. Now, here's what we do next. We're going to say, all right, one of these legs here in the right triangle is going to have a length of x. The other one then, the other leg, since it's congruent to the first one, would have to have the same length here as x. But every time we do this, there's something cool that works out with the length of the hypotenuse. Now, you might not want to write down what I'm about to put here just yet, but at least temporarily, I'm going to put an h there for hypotenuse. And I'm going to set up the Pythagorean theorem. You guys don't need to write this down, but it's leg squared plus leg squared is equal to your hypotenuse squared. And now what I want to try to do is see if there isn't some way algebraically that we can determine the length of h in terms of x, which was what we used on the other two sides. That means I'm going to take this equation now, and I'm going to try to solve it for h. Well, the first thing I'm going to do is add together x squared plus x squared to get 2x squared, and that is equal to h squared. And then if I'm solving for h, I'm going to try to take the square root of the right and the square root of the left. Now let me switch sides here on you guys. The square root of h squared just becomes an h. When we try to take the square root of 2x squared, remember everybody, we can split that up into the square root of 2 multiplied by the square root of x squared. And now, the square root of x squared becomes x. You can't do anything with the square root of 2, so here's what we got, guys. h, the hypotenuse in this triangle, is equal to x multiplied by the square root of 2. So what that means is we now know a pattern, basically, that in any right triangle, any 45-45-90 right triangle, the legs are going to be x and x, the same number twice, and the hypotenuse is always going to be whatever x is, but then multiplied by the square root of 2. So these three numbers here, guys, and they are numbers, x, and x root 2, that's something that you guys are going to have memorized here pretty quickly for the side lengths in a 45-45-90 right triangle. And a lot of your homework then is going to be dealing with that. And I'm going to give you guys some practice at that a little bit later on right here. But for now, let's go ahead and talk about answering these three questions here. How does trigonometry relate to this special right triangle? So let's set up the sine of a 45-degree angle. Doesn't matter which one you go with. Let's put u standing right here then, guys. And sine is your opposite leg, which is x, divided by your hypotenuse, which is x over the square root of 2. Now what happens here, guys? A couple of cool things. First of all, x and x are identical factors. They just divide each other out. So we would really now end up with 1 over root 2. And actually, that's not incorrect. In fact, I'm going to write that out. 1 over root 2, but then usually we will rationalize that by multiplying it by root 2 over root 2. And so we're going to land on this value, which is one you guys need to be familiar with. The square root of 2 divided by 2. 2. That's the value we really should know for the sine of 45 degrees. Now, if you wanted to test this, everybody, you could grab your calculator and you could ask it, what is the sine of 45? And your calculator probably gives you 0.707106781. Now, if I were to type in this same fraction into my calculator, let's see what that is when I get that as a decimal. The square root of 2 divided by 2, yep, gets me the exact same decimal again. But this value here is the exact value of the sine of 45 degrees. This isn't one that we want to spend time trying to memorize at all. Okay, how about what's next, guys? Cosine of 45 degrees. Cosine is adjacent leg over hypotenuse. Well, this is going to look familiar. It's, again, x divided by x root 2. And once more, the x's cancel out, leaving you with 1 root 2. But once again, you rationalize that and end up with the same value here of root 2 over 2. So the sine of 45 degrees and the cosine of 45 degrees have the exact same value. And that's because the opposite leg and the adjacent leg in a 45-45-90 are exactly the same length because it's isosceles. Tangent of 45 is the coolest one of all of them, though. Tangent is opposite leg over adjacent leg. So from your angle right here, the opposite leg is this x, the adjacent leg is this x, and it doesn't matter what x is, x divided by x is always going to equal 1. So these are three values we would want to have memorized, guys. The sine of 45 is root 2 over 2. The cosine of 45 is also root 2 over 2. And the tangent of 45 degrees is just plain 1. And what I want you guys to notice here, though, is in all three of those answers that we just came up with, there's no x, meaning that the value of x has no bearing at all on what you're going to get for the sine or cosine or tangent of a 45-degree angle. Okay, we're going to do that same thing again now, everybody, except this time we're going to work on the second type of special right triangle, which is a 30-60-90. And that pattern I have drawn for you already over here on the side. In a 30-60-90, again, it's named as such because of its angle measures. A 30-degree angle right here, a 60-degree angle here, and then, of course, a 90-degree angle, which makes it a right triangle. And the side lengths then are x. That is the shortest side, and it's the one that's across from the 30-degree angle. X is the shortest side. The hypotenuse, then, is always twice as long as whatever x was. So this is just 2x. And the longer leg, which is the middle length of all of the sides, is going to be whatever x is, but then we multiply x by the square root of 3. And if you really want to know where this all comes from, guys, it really deals with the concept. I wouldn't put this in your notes, guys. It really deals with the concept right here of an equilateral triangle. 60, 60, and 60. And in that type of triangle, all three side lengths are the same. So I'm going to name this one 2x. You'll see why in a second. And this would be 2x, and this would be 2x as well. And then what we do is we bisect one of those angles by drawing an altitude straight down to the bottom, 90 degrees. And we cut this 60-degree angle in half, and there's your 30-60-90 triangle. Now, this bottom side had a length of 2x, but we cut that in half as well. So x is the length of just that short piece on the bottom of the triangle. So that explains why in our 30-60-90, the hypotenuse is 2x and the short leg is x. That should explain this and this. Where does the x root 3 come from? Well, just like I did in the previous problem with a 45-45-90, you could name this missing piece. I might call that b here, and we'd get something like x squared plus b squared is equal to 2x, which we would need to put in parentheses, squared. And going real quickly here, guys, you'd get x squared plus b squared is equal to 4x squared. Subtract the x squared and get b squared is 3x squared. Take the square root of both sides, and that's how you end up with b is x times the square root of 3. So that explains where that comes from. Okay, so with all that in mind, let's answer a few questions. And I realized I should have gotten rid of all that before we started this, so let's get rid of it. Okay, here we go, guys. Let's knock out a few questions right here. Sine of 30 degrees. Okay, so from a 30-degree angle, you are standing right here, and sine is your opposite leg over your hypotenuse. So from where we're standing, the opposite leg is x, and the hypotenuse is going to be 2x. What simplifies here? Just like on the 45, 45, 90 we did a moment ago, all the x's cancel, leaving you with a 2, but in the denominator of your fraction. So the sine of 30 degrees is 1/2. And if you wanted to verify that, go to your calculator, type in sine of 30, and it's going to give you 0.5, which of course is the same thing as 1/2. Shifting gears here, guys, I'm now asking you for the cosine of 60 degrees. So I got to take our little stick figure dude and move him over here. Now you're standing at that spot. Cosine of 60 means adjacent leg over hypotenuse. Well, the adjacent leg here is this same x that you just used for your opposite leg from 30 degrees. So from the 60-degree angle, your adjacent leg is x, your hypotenuse is still 2x, and once more the x's cancel, leaving you with a 1/2. I wanted you guys to see right here that the sine of 30 degrees and the cosine of 60 degrees are actually the exact same angle. That's opening up the door to something coming later, but I think I'll leave it unsaid for now. How about the sine of 60 degrees? So your stick figure is still right here. Sine is the opposite leg, which is x times the square root of 3 divided by the hypotenuse, which is 2x. The x's cancel again, and we're going to end up then with this weird number, root 3 over 2. And that's one you guys are going to need to know pretty well by the end of this chapter here as well. And I put one more right here, and I guess that's all I did with you guys. Let's do the tangent of 30 degrees. Okay, so we're got to move the stick figure, there we go, back over here to 30 degrees. And tangent means opposite leg over adjacent leg. So from the 30-degree angle, our opposite leg is going to be x, and our adjacent leg is going to be x root 3. Once more, the x's cancel, and that leaves you then with 1 over the square root of 3. Now that's not incorrect, but normally at this level, we rationalize our denominators. So I'll multiply that by root 3 over root 3. And that means that my numerator is going to be 1 times the square root of 3, which is root 3, and my denominator, root 3 times root 3, is just 3. So that's the commonly accepted form of the value here for the tangent of 30 degrees. Okay, so that's what a 30, 60, 90 looks like. And I'm not going to go through this, so don't put this in your notes here, guys. But with where we're going here and where you're going to need to be if you're going to be successful at higher level math courses like pre-calculus or calculus, this is a table you guys are going to have to be able to fill out. You're not necessarily going to have everything memorized, but there are methods then by which you guys can kind of think about some of the angles that we just talked about and fill this in. So this is coming down the pipe here a ways, but I think we can leave that out for now. What I really want to get into now, guys, is this batch of, I think I've got 4 problems for you right here, where we are, here's the phrase, solving right triangles. And what it means to solve a right triangle is this. Find the measurement of everything that's missing within this problem. Although I'm actually easing you into it, and for right now, for example A, I'm only having you find a missing side. But by the end of this, we're going to be doing a little bit more work. Okay, let's take a look at what's going on in this problem here, everybody. What we have is a right triangle, and 3 measurements have been given to us. A hypotenuse of 14, one of the acute angles of 60 degrees, and then the right angle here of 90. Now, the first thing I would hope you guys recognize is that this is one of the special right triangles we just talked about. This is a 30, 60, 90. You could verify that by taking 180 minus the 60 and minus the 90, but sure enough, that would work. And what I need you guys to understand is that special right triangles, like a 45, 45, 90 or a 30, 60, 90, these problems can be solved without using your calculator. Let's talk about how. So what we need here in order to do this, oh, I made a mess of this. All right, is we needed this big pattern right, oh, that's horrible. This big pattern right up here at the top. That in a 30, 60, 90 triangle, your side lengths are x for the short leg, x root 3 for the long leg, and 2x for the hypotenuse. So how do we use that in a case like this? All right, let me go ahead and write this out here, guys, that if the short leg is x, the hypotenuse is 2 times that. If I knew the short leg and I wanted the hypotenuse, we would multiply by 2. But as this one works, we're going backwards the opposite direction. So to go from the hypotenuse to the short leg, we're going to divide by 2. And that tells us, without doing any real work right here, that x has to equal 7. If the short leg were 7, we would double that to get the hypotenuse of 14. Now, the next thing to take from that, guys, is that from the short leg, you can always go to the long leg here by multiplying by the square root of 3. That's how we went from an x to an x root 3 right over here. So if x is 7, y is simply going to be 7 multiplied by the square root of 3, which is 7 root 3. Can't be simplified any more than that, and that's our answer here for example 4a. So we took the hypotenuse of 14, cut it in half to get 7, and then multiplied by 7 by root 3 to get the long leg of root 3. Okay, let's do one with a 45, 45, 90. Not sure if you'll find this one easier or harder, but let's take a look. Now again, as soon as you match up 2 of the 3 angles with one of the specials we talked about, you know you're good, guys. 90 degrees, 45 degrees, yep, the other angle would have to be 45 degrees as well, which makes this a 45, 45, 90, which makes it isosceles. These 2 sides have to be congruent to each other. Now, in an isosceles right triangle, a 45, 45, 90, to go from the short leg, or either leg I should say, to the hypotenuse, we're going to multiply by the square root of 2. That means that to go backwards now, you guys, from hypotenuse to one of the legs, we reverse that process and we're going to divide by the square root of 2. So to come up with the value of x, we're going to take our hypotenuse, which is 18, and divide it by the square root of 2. And again, we'll try to rationalize this by multiplying by root 2 over root 2. So what does that do for us, guys? X is now 18 root 2 all over root 2 times root 2 is 2. And now we can divide a 2 out from the 18 and the 2. And that's going to leave us with an answer here of 9 times the square root of 2. Just a 1 in the denominator, guys. So that's our value for x, 9 root 2. So we took the 18, which was the hypotenuse, and divided by the square root of 2 to get x. And now the really fun part. How long is y? Well, again, guys, because this is a 45, 45, 90, we know that this triangle is isosceles. The legs, x and y, have to be congruent. So whatever we got for x, we'd end up with the exact same value here for y, and we're done with example B. Okay, not too bad. However, not every triangle you guys are going to see is a special right triangle. So let's talk about one that looks like this. Okay, so in this problem, I've given you a right triangle called ABC, and I've given you 3 measurements. That's always the key. A leg of 7. A right angle, so there's a 90 degree, and then one of the acute angles here is 36 degrees. Now, when the directions say to solve a right triangle, what that really means is find the measure of everything that wasn't already given to you. And that's what I did here for you. I probably shouldn't have, guys. Sorry, you're going to have to do this part on your own. What are the 3 things that we're going to need to know? We're going to need the measure of angle A, which we call capital A, and then the length of these 2 sides right here, little a and little c. So let's talk about how to do that one. Capital A is probably the easiest. Once again, we know, everybody, that all 3 angles in a triangle have to add up to 180. So if you want to find the measure of angle A, I would do this in one step. I'd start with 180 and I'd subtract the 2 angles that you do know. There was a 90 degree angle at C and a 36 degree angle at B. So go ahead and type that into your calculator. Pretty sure we're going to end up with 54 degrees now for the measure of angle A. Nothing too fancy about coming up with that. But right now is when this problem gets a good bit harder. Now, everybody, we are finally, for the first time, going to talk about the most useful and tangible benefit of trigonometry. If finding missing sides and angles in right triangles that are not specials. Let's talk about what we mean right here. We want to try to find little a right here. So What are we going to do with that, guys? I think what we're going to do here is let's use this 36-degree angle right here. So from that 36-degree angle, the 7 over here is the opposite leg within this triangle. And the A that we're trying to solve for, that one is actually going to be the adjacent leg, given that we're standing right here at B. So the question now is, we should always think about our old buddy here, SOHCAHTOA. Out of the 3 basic trigonometric ratios, which of the 3 uses opposite leg and adjacent leg? And that would be tangent. So we're going to write out a tangent equation. Tangent. And guys, you never write sine or cosine or tangent without an angle coming right after it. Tangent of 36 degrees is equal to, and again, TOA. Tangent is opposite leg over adjacent leg. So from the 36-degree angle, the opposite leg is 7. And the adjacent leg is unknown. That's our A. And this is how you set up a trigonometric equation that we're now going to have to solve for A. And I started you with a hard one right away because the variable here, you guys, is located on the bottom of your fraction. The next one we're going to do, I think, is a little bit... Nope, I lied. It's just as complicated. Okay, I'm going to teach you guys one quick shortcut, though, for what to do. When the variable is on the bottom of your fraction, you're going to take this denominator and what is really the numerator of the opposite side, and you're just going to flip-flop those two. We're going to end up now with A is equal to 7 divided by the tangent of 36 degrees. And now that's isolated the A, we should be able to go to our calculator and type this in just the way it looks on our paper. Stacked fraction, 7 on top, and then a tangent of 36 degrees on the bottom. Now before I hit enter, I want you guys to think, should little a be more or less than the 7 that we came up with right here? Well, I think just about everybody's going to give me the right answer here. A should be bigger than 7, but the reason might not be right. It's not because A looks bigger than 7. It's because we have a 54-degree angle here at A and only a 36-degree angle at B. That means that the side opposite from the 36-degree angle, 7, has to be the shortest side. A has to be bigger than 7 because 54 is bigger than 36. Okay, moment of truth, everybody. 7 divided by the tangent of 36, I got 9.63. We'll go just to 2 decimal places here for the measure of side A. 9.63. All right, and I'll draw a line right there because I think we're done with that part. Okay, on to the third part now. Let's find the measure of C. Now, I'm still going to use the same 36-degree angle I used a second ago. I don't want to use A in my calculations to find C because I'm not 100% sure that this answer is accurate. And if I made a mistake in finding little a and then I used it to find C, that would guarantee to be wrong as well. So let's keep using the 7 over here. So again, from the 36-degree angle, the 7 is the opposite leg and the C is the hypotenuse. So which trig ratio uses opposite leg and hypotenuse? That's going to be sine. So the sine of 36 degrees equals an opposite leg of 7 and a hypotenuse of C. Now, just like the last problem, the variable ended up on the bottom of a fraction. So I'm going to switch the bottom right and the top left. And we're going to get C is equal to 7 divided by the sine of 36 degrees. So let me type that into my calculator. But while we're doing that, guys, let's think long and hard. How big should C be? What I'm hoping you recognize is C is the hypotenuse of this triangle. It has to be the longest side. It's got to be longer than 7, but it also needs to be longer than the 9.63 that we came up with for A. If it isn't bigger than both of those numbers, we know we've done something wrong. So again, stacked fraction on the calculator, and this is now 7 divided by the sine of 36 degrees. And I'm hoping for something bigger than 9.63. Yeah, we got 11.63. 0.91, and that's what I'm going to put right there for little c. So guys, that set of three answers right there is what it looks like when you've solved a right triangle. Three measurements were given to you in the diagram: the measure of angle B, the measure of angle C, and the length of side B. We've now come up with the measures of everything that wasn't given to us: capital A, and little c. And I just have one last thing to do with you. This won't take that long. Here we're not going to solve the entire triangle. We're just going to solve for x, although I just realized you couldn't do this problem unless I told you that that was a right angle there. Now, unlike the last problem right here, in which you were given, let's go back to this, you were given two angles, a 36 and a 90, and one side length, which was 7. Here, you're given two side lengths of 5 and 11, and only one angle measure, and that's 90. So how do we handle this one? All right, we're going to try to find this angle right here. So that's where you're standing. And let's think about sides, guys. The 5 is the leg across from you. That's the opposite leg. The 11 is the leg right next to you. That's the adjacent leg. And which trig ratio uses opposite and adjacent? That's tangent. Now, it's tangent, and let me repeat something I said about 5 minutes ago, guys. Every single time in your life when you write down sine or cosine or tangent, it has to be followed by an angle measure. Now here, the same thing applies, except the measure of our angle here is the unknown. That doesn't matter. The angle is x degrees. So in this case, the variable is the angle. The tangent of x is equal to, all right guys, I'm going to leave some room here. Tangent is opposite leg over adjacent leg. That's 5 over 11. Now, how do we solve an equation that looks like this? Well, as I've been telling you guys all year, identify your variable, obviously there it is, figure out what's being done to it, and then undo that with an inverse operation on both sides of the equation. So the question now is an interesting one. What is being done to x here? And the wrong answer that a lot of people want to give me is that x is being multiplied by tangent. Just like when we did logarithms back in chapter 7, everybody, logarithms are not multiplication. It's a separate operation all by itself. Well, tangent is an operation too. And there's only one operation that will undo tangent. There's only one thing that's the inverse operation of tangent. And they called it, not very creative, inverse tangent. So what we're going to do is out in front of that, we're going to write a tangent and then what looks like a -1 power. And we're going to take the inverse tangent of the left-hand side. Can we do that? Sure, as long as we do the exact same thing on the right side as well. And once more, guys, just like logarithms, this inverse tangent needs to be in front of the 5/11ths. It wouldn't make any sense to put the 5/11ths and then the inverse tangent after that. It's got to be in front. Now, as you might have guessed already, the inverse tangent and the tangent on the left side cancel each other out, and we just get x. Now on the right side, we want to know what's the inverse tangent of 5/11ths. What we're really going to ask our calculator is what angle out there has a tangent ratio of 5 over 11. So you guys are going to hit second on your calculator and then the tangent button. So you should get something then that looks like inverse tangent, and then type in 5 over 11, either as a fraction or just with using the division key. And if we're all on the same settings right here, we should have gotten 24.44 degrees, and that is the value right there of x, everybody. We took the inverse tangent of 5 over 11, and it's a 24.44 degree angle that makes that work. From there, I think you guys could probably figure out the measure of this other angle right over here by subtracting from 180, and we could probably use SOHCAHTOA, sine, cosine, or tangent, to come up with the length of our hypotenuse, or the Pythagorean theorem for that matter, but I think I'm going to leave it right there. All right, guys, that is everything we needed to cover from 13.1. It's a really long section because it's a recap of basically a whole chapter of geometry last year, kind of in one nutshell right there. Hopefully a lot of that is coming back to you here, and I think as you dive into your homework on 13.1, I think I have 2 worksheets for you here. Hopefully you're going to remember how to do most of that. All right, good luck, everybody, and let us know when you have some questions.